Chapter 9.7 Systems of Many Particles. The outline of this video is as follows. We will begin by defining the velocity and total momentum of a system of particles by focusing on its center of mass. Then, we will find the acceleration of the center of mass, which allows us to formulate Newton's second law for the entire system. Building on that, we will generalize the impulse momentum theorem to describe how external forces change a system's total momentum over time. This leads us to a crucial result, the principle of conservation of momentum for an isolated system. Finally, we will solidify our understanding by working through several applications and examples. Now that we have an expression for the position of the center of mass, we can find its velocity, which helps us describe the motion of the system as a whole. We begin with the definition for the position vector of the center of mass, RCM. To find the velocity, we take the time derivative of this entire equation, assuming that the total mass of the system, m, remains constant in velocity. From basic kinematics, we know that the time derivative of position is velocity. Therefore, the derivative of the center of mass position drcm dt is simply the velocity of the center of mass, vcm. Likewise, the derivative of each individual particle's position, r sub I, is its individual velocity, v sub I. The resulting expression shows that the velocity of the center of mass is equal to 1 over the total mass, multiplied by the sum of each particle's mass times its velocity. In short, the velocity of the center of mass is the mass-weighted average of the velocities of all the particles that make up the system. We can now use the velocity of the center of mass to define the total momentum for an entire system of particles. This is a crucial step that allows us to treat a complex system as if it were a single object. Starting with the equation for the velocity of the center of mass, if we multiply both sides by the total mass of the system, m, we arrive at a very useful result. The left side of the equation becomes the total mass, m times the velocity of the center of mass. The right side becomes the sum of the individual momenta, that is, the mass of each particle times its velocity. By definition, this sum is the total linear momentum of the system, which we can call P total. This leads to a powerful interpretation. The total momentum of the entire collection of particles is exactly equal to the momentum of a single, imaginary particle that has the total mass of the system and moves with the velocity of the center of mass. So, the key takeaway is that the total momentum of a system is simply its total mass multiplied by the velocity of its center of mass. Now that we have an expression for the velocity of the center of mass, we can find its acceleration by taking a time derivative. This is a crucial step because acceleration connects the motion of the center of mass to the forces acting on the systems. Equation 9.37 shows this process. Differentiating the center of mass velocity with respect to time gives the center of mass acceleration a sub cm. On the right side of the equation, the derivative of each particle's velocity, v sub I, becomes that particle's acceleration, a sub I. Next, we can rearrange this result by multiplying both sides by the total mass, m, which leads to equation 9.38. The left side is now the total mass times the center of mass acceleration. Using Newton's second law, we can replace each term m sub I times a sub I on the right side with F sub I, which is the net force on that specific particle. This net force includes all interactions, both from within the system and from outside of it. The result is that the total mass times the center of mass acceleration equals the vector sum of all forces on all particles in the system. We can now simplify the relationship between force and the acceleration of the center of mass. This is a powerful step because it allows us to describe the motion of a complex system of many particles in a very simple way. First, recognize that the total force on a system is the sum of all forces on all particles. These forces can be either external, coming from outside the system, or internal, which are the forces particles within the system exert on each other. The key insight comes from Newton's third law. For any pair of particles, the internal forces they exert on each other are equal and opposite. When we sum all forces across the entire system, these internal action-reaction pairs cancel out completely. This leaves only the external forces. The result is a version of Newton's second law for a system of particles. The net external force equals the total mass of the system multiplied by the acceleration of its center of mass. In short, the center of mass moves just like a single particle, under the influence of only the external forces. Let us now generalize the impulse-momentum theorem to cover a system of many particles. This is a crucial step because it allows us to analyze how the motion of an entire collection of objects changes when subjected to external forces over a period of time. We begin with Newton's second law as it applies to a system. The net external force equals the total mass times the acceleration of the center of mass. By integrating both sides of this equation with respect to time, we can find the effect of a sustained force. The integral of the net external force is, by definition, the total impulse imparted to the system. The integral on the right side simplifies to the total mass multiplied by the change in the velocity of the center of mass. Because the total momentum of the system is the total mass times the center of mass velocity, this quantity is exactly the change in the system's total momentum. This leads to our final result. The change in a system's total momentum is equal to the net external impulse applied to that system. This is the cornerstone of the non-isolated system model for momentum. This slide introduces a fundamental principle: the conservation of linear momentum for a system of particles. We call a system isolated when the net external force acting on it is zero. Since the net external force determines the acceleration of the system's center of mass, an isolated system has zero acceleration for its center of mass. This directly implies that the velocity of the center of mass must be constant, because the total momentum of the system is just the total mass times this constant velocity. The total momentum is also conserved. For example, consider a swimmer and a raft, initially at rest. When the swimmer dives off, the raft moves in the opposite direction. The individual parts move, but they do so in a way that keeps the center of mass of the entire swimmer-raft system exactly where it started. The total momentum of an isolated system does not change. This quiz tests our understanding of momentum conservation for a system of many particles. We will analyze how the motion of people inside a cruise ship affects the ship's overall speed. First, let us consider what happens while the vacationers are running toward the stern. Our system is the ship plus all the people. Assuming no net external horizontal force, the velocity of the system's center of mass must remain constant. As the people move backward, they gain momentum in that direction. To keep the total momentum of the system unchanged, the ship must gain an equal amount of forward momentum. This means the ship temporarily speeds up. Now let us look at the situation after they have stopped running. We are comparing the final state to the initial state, before they ever started. In both the initial and final states, the people are at rest relative to the ship. Because the total momentum of the isolated system is conserved, the final velocity of the ship must be the same as its initial velocity. The only thing that has changed is the distribution of mass within the system, not its total momentum. Therefore, the ship's speed is ultimately unchanged. This example explores what happens to the center of mass of a projectile that explodes in midair. The key insight is that internal forces cannot change the motion of a system's center of mass. When the projectile explodes, the forces pushing the fragments apart are internal to our system, which is the collection of all fragments. These forces are powerful, but they all come in balanced action-reaction pairs, so their net effect on the system as a whole is zero. The only external force acting on the system, both before and after the explosion, is gravity, assuming we can ignore air resistance. Because the net external force is unchanged, the acceleration of the center of mass is also unchanged. Imagine a firework, she will. Even after it bursts, the average position of all the sparks continues to trace the same parabolic arc. Therefore, the center of mass of the fragments follows the exact same path the projectile would have taken if it had never exploded. This slide presents figure 9.21, which provides a clear visual for the exploding projectile example. The dashed line represents the parabolic trajectory the projectile would have followed under the influence of gravity alone had it not exploded. At some point along this path, the projectile breaks into several fragments. The forces that cause this explosion are internal to the system of fragments. As we have learned, internal forces cannot change the velocity of a system's center of mass. Notice the red dot, which represents this center of mass. It continues to travel along the original dashed line path, completely unaffected by the explosion. This happens because the only net external force acting on the system is gravity. In short, the center of mass of the fragments follows the exact same path the intact projectile would have. Now let us apply our understanding of the center of mass to find where the second piece of the projectile lands. We know the system's center of mass must land at the original range, r, exactly where the projectile would have landed if it had not exploded. The problem states that the projectile splits into two pieces of equal mass, and that one of these pieces lands at a position of 2 times r. Our goal is to find the landing position of the other piece, which we will call x2. We use the standard formula for the position of the center of mass. As shown on the slide, this position is the sum of each mass times its position, divided by the total mass. Since the two masses are equal, this formula simplifies to the average of the individual landing positions. Therefore, r must be equal to the quantity 2r plus x2, all divided by 2. Solving this simple equation for x2, we find that x2 must equal 0. This surprising result means the other piece lands right back at the launch point. We will now apply the principle of momentum conservation to solve a two-dimensional explosion problem. The goal is to find the velocity of a missing fragment after a rocket explodes in mid-air. Let us first outline the physical situation. Initially, we have a single rocket moving vertically upward at 300 meters per second. This is our initial state. The rocket then explodes into 3 fragments of equal mass. This explosion is caused by internal forces. For our final state, we know the velocity of 2 of the 3 fragments. The first fragment moves upward at 450 meters per second, and the second moves horizontally in the positive, x, direction at 240 meters per second. The key insight for solving this problem is the impulse approximation. Because the explosion happens over a very short time interval, we can ignore the effects of external forces like gravity during the event. This means we can treat the rocket and its fragments as an isolated system. For an isolated system, the total linear momentum is conserved. Therefore, we can find the velocity of the third fragment by setting the initial momentum of the single rocket equal to the vector sum of the final momenta of the 3 fragments. We can find the velocity of the third fragment by applying the principle of conservation of momentum. Because the explosion involves only internal forces, the total momentum of the system right before the event must equal the total momentum of all the fragments right after. The initial momentum is the total mass m times the initial velocity vector, vi. The final momentum is the sum of the momenta of the 3 equal mass fragments. Our conservation equation is m times v I equals the quantity m over 3 times v1 plus m over 3 times v2 plus m over 3 times v3. Notice that the total mass m is in every term, so it cancels out. We can then rearrange the equation to solve for the unknown velocity, v3. 3. This gives us that vector, v, 3 equals 3 times vector, v, I, minus vector, v, 1, minus vector, v, 2. Substituting the given values, we get 3 times 300j hat minus 450j hat minus 240i hat. The final result for the third fragment's velocity is negative 240i hat plus 450j hat in meters per second. This vector tells us that the third fragment moves both west and upward. Let us summarize the powerful concept of the center of mass, which simplifies the analysis of complex systems with many particles. The central idea is that the center of mass moves as if it were a single particle that contains the total mass of the entire system. The total linear momentum of the system is this total mass multiplied by the velocity of the center of mass. This leads to a system-level version of Newton's second law, where the net external force on the system equals its total mass times the acceleration of its center of mass. We only need to consider external forces, because all internal forces, which occur between particles within the system, cancel out in action-reaction pairs. This framework gives us a crucial conservation law. If the net external force on the system is zero, the system is considered isolated. For any isolated system, the total linear momentum is conserved, which means the velocity of its center of mass remains constant. Let us apply our knowledge to these two conceptual questions, which highlight the conservation of momentum and the behavior of the center of mass. For the first question about the firecracker, remember that the system is initially at rest, so its total momentum is zero. Since the ice is frictionless, there are no external horizontal forces. This means the total momentum of all the pieces after the explosion must still add up to zero. Piece A moves west, and piece B moves south. The vector sum of their momenta points southwest. To cancel this out and keep the total momentum at zero, the momentum vector for piece C must be equal in magnitude and opposite in direction. Therefore, piece C must move in a generally northeast direction. For the second question about the cruise ship, the key is the center of mass. The system is the ship plus the vacationers. With no external horizontal forces, the center of mass of this system cannot move. As the people run toward the stern, their mass shifts backward relative to the water. To keep the overall center of mass stationary, the ship must move forward. When the people stop running, the ship also stops. But it is now at a new position, slightly ahead of where it would have been.